Supplemental math videos from Circle Christian School. Welcome to the season premiere of Radical Dudes and Irrational Offenders. Welcome to the radical prison, where being a twin is a good thing. Irrational offenders are those radicals that cannot be placed on the number line. But simplifying them really does help. When we evaluate radicals, that means we're going to use a calculator, and of course it's going to be some sort of non-repeating, non-terminating decimal. Simplifying radicals means that we're going to have to use those little factor trees. Okay, now our radical dudes are those radicals that are perfect radicals. For instance, the square root of 81 is 9, square root of 225 is 15, and the square root of x squared is x. Our irrational offenders, for instance, we have the square root of 8. He's not perfect. That we know it's in between the square root, perfect square root of 4 and the perfect square root of 9, which means that it's going to be somewhere between 2 and 3, or 2 point yada yada yada, where the decimal is going to be rather high because it's really close to the 9. Square root of 24, of course, is going to be between 4 and 5. So it's 4 point yada yada yada. And again, it's going to be a high yada 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 because 24 is very close to the 25. 108 is somewhere between 10 and 11. It's going to be 10 point yada yada, but the yada yada here is going to be lower because it's closer to 100. All right, let's work with the factor trees here. Now there are two ways actually to take these irrational offenders, these irrational radicals, and make them simplified. And again, simplified means what we're trying to do is pull out as many perfect radicals as possible and leave the least amount of non-perfect guys inside. Two ways to do it. If you're a really great factor freak, be my guest. So for instance, if I was to look at 24, two things that I would look at would maybe be 4 and 6, knowing that the 4 is a perfect radical. Let's split it up, have the square root of 4 times the square root of 6, and square root of 4 we know is 2, and then we end up with a 6. That's one way. The factor tree is another way to go and do it. With the factor tree, we're just going to find these perfect radicals, these prime numbers. That's why they're called prime factorization trees. And again, we can take the 4 and the 6. You can use 3 and the 8 or 2 and the 12. They're all factors. It just, means that the branches are a little bit different from tree to tree. Neither one of these are prime, so we know we're not done yet and we have to keep branching. So now I need two factors for 4, which is 2 and 2. And seeing that they're prime, I'm going to circle them. That just keeps me from 1, losing them, and 2, knowing that I don't have to do any more branches. 6 is 2 and 3. And again, all these are prime numbers. So I'm just going to circle them. Now it takes 2, because it's a square root here, of any one number for it to be able to escape. We have 2 2's right here, so that means 1's going to come out, and there are no twins with the 2 and the 3, so they have to stay inside. Since they're factors, it's 2 times 3, and we get 6. And lo and behold, it's the same number that we had before. Okay, 108. Another one, not perfect. We know it's between 100 and 121. That we can break it up into factors again if you're a really good factor person. Let's see, I know 12 and 9. Okay, we got a good one, but 12 possibly may have to be broken up just a little bit more. And we know we have 4 times 3. And so we have the square root of 4 times the square root of 9 times the square root of 3, And we know the square root of 4 is 2, the square root of 9 is 3, times them together and we get 6 square root 3. And again, if you are just fabulous with factoring, that go ahead and do it this way. The other way is to do the prime factorization trees, break it down into prime things. So I'm going to break the 12 and the 9 up. Neither one of them are prime. And we have a 4 and a 3. It could be a 2 and a 6. Doesn't matter. I'm going to make some prime numbers out of it. So we have some 2's. And then we have 3 and 3. And of course, what we're basically saying that if we took the 2 here and multiplied it to the 2 and multiplied it to the 3 and the next 3 and the next 3, if we multiplied all these primes together, we would get 108. So it is a prime factorization. But here again, all we need are the twins. So we have a pair of 2's, he comes out, a pair of 3's, he comes out, and we have a 3 left over right here. And so we just have the square root of 3, and we get 6 square root 3. Now to double test this back, to go back into the prison, to get your prison pass to go back in and visit the 3, the 6 would have to square itself to go back inside, and 6 times 6 is 36. And when you multiply 3 to 36, you get 108. The same process happens with radicals that are not square roots. And so we're going to, the only difference here is that because we have an nth root of 3, it means that we need triplets for one of them to come out, 3 of a kind. So I'm going to take 625, which we know can all at least be divided by 5. It's a nice place to start. So if I divide that by 5, I'm going to get 1, 2, and 5. So 1 and 25. 5's prime. 125, again we can do the 5, and we get 5 and 25, and the 5's prime. And sometimes branches kind of go sideways. Branches kind of go sideways, so we can do that, and the roots kind of follow them. And we end up with 5 and 5. And we're looking for triplets. And let's see, we have a 5 and a 5 and a 5. So the 5's going to go outside. And we have a 5 left over. Now we can also do this as a factor radical instead of doing the prime factorization. I do happen to know that 25 times 25 is 625. We're going to have to break that up a little bit more. So, let's see. We know we have 5 times the 5 times 5 times the 5. Okay, I kind of missed my point here, but it's okay. No problem. And we can see that we've got 3 of them again, so a 5 can come out. Forgot my little cube here. Happens to the best of us. You're going to forget that cube and 4th root and all those kind of things. So we have a 5 that comes out and a 5 comes inside. One of the other things that I happen to know about 625 is that it's 5 times 125. Here's my little cube again. And I happen to know that 125 is a perfect cube, so it's going to come out and it leaves a 5 inside. Something that you should probably learn, and I'm going to hit the eraser here. Remember, anytime something disappears before you want it to, just stop it, roll the tape back a little bit, and rewatch it again. It's what I do when I have to watch, tapes about certain types of math things too. It's like, oh, what did they say? I just roll it back. That your perfect cubes, for instance, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. I suggest that you know all of those also too. It'll save you a lot of time. And obviously the cube of all those is just the work way backwards. Let's take a look at the letters. If we can cube root or square root or any root numbers, we can also do it to letters, variables. After all, they're just real numbers. These are all going to be square roots. And so we have an x times an x here, which is twins, so we know an x comes out. When it's 3, we got triples here, and it takes 2 for 1 to come out. So we're going to have 2 with 1 staying inside. 4 means that there's 2 ways to look at this. We did it in class with an x times an x times an x times an x, but it's also the same thing as x squared times x squared. And we already know that the square root of x squared is x, so we would have x times x, or x squared. Next one would be that we have the x squared come out, leaves 1 inside. X to the 6th power. Now remember, this is a square out here, and perhaps you're beginning to see a pattern here with the index, that if you take the number on the inside and divide it by the index on the outside, you're going to get the root. So if we had 12 in the 2, 12 divided by 2 goes evenly 6 times, we'd have x6. Likewise, 25 divided by the 2 goes at least 12 times, so we'd have an x to the 12th power. This is just things to do with exponents. Radicals are basically the inverse of exponents. That 25 divided by 2 is 12 with 1 left over, and he's the guy who stays inside. Alrighty, let's go mix it up now. Let's have numbers and letters. Alright, this isn't any different than anything else I've ever told you before. It's numbers to numbers, letters to letters, and in all honesty, when we get to it, it's going to be binomial to binomial. Oh, don't let that scare you. It's just the same thing that you've always done. It just takes 2 because we have a square root. Cube root takes 3. Fourth root takes 4. And so forth and so on. My suggestion to you is to do that expand thing. If these are something that you're still getting a little bit used to. And so what I've done is square rooted the numbers, and then I've square rooted all the letters, and I'm just going to work with them individually. Now the square root of 12, which you could do 3 and 4, is just a good one to learn that it's always 2 to the square root of 3. Remembering that the square root of 8 is 2 to the square root of 2. These are 2 good ones to just learn. And then x cubed would be 3 divided by 2 goes evenly once with 1 left over. Y squared, 2 divided by 2 leaves us with 1. And z, 7 divided by 2 goes evenly 3 times with 1 left over. And now we're just going to put these all together, the guys on the outside and the guys on the inside. So we have a 2, a x, a y, and a z3. So we have 2 times x times y times z3. And now we're going to do the inside guys. I'll do that as a different color. 3, x, and a z. So we have 3, x, and a z. See, it wasn't that scary at all. In fact, it was rather friendly. It was so friendly that what you want to do is draw a radical happy face.